So today we're going to be talking about different ways to organize quantitative data. So just a refresher on what quantitative data is. Remember, these are the numbers, numerical. Or a quantity, hence quantitative. Then there's the two types of quantitative data. Discrete is the countable, so like number of something. And then continuous quantitative data is the measurable data. So like height or weight or distance, time, anything that you measure. Okay, so the thing with quantitative data is that it can't be put directly into frequency tables since they don't have obvious categories. Like with our qualitative data, the categories are pretty simple. It's just whatever the choices were when you were gathering data. With quantitative, all of the answers you're getting are numbers, so you have to figure out kind of how to sort them or how to split them up. So the categories that we use for quantitative data are called classes or intervals of numbers. You're going to have like a range of numbers, and then you'll count how many of your data values are in that range or that interval. So when we have a class, the first number of the interval is the lower class limit, it's the lower number, and the second number of an interval is called the upper class limit. It's the upper number or the higher number. And then the difference between two successive lower class limits is called the class width. So an example, if we had our data and we were going like from 0 to 9, and then 10 to 19, and then 20 to 29. So these were our classes. These first three numbers, the 0, the 10, and the 20, these are the lower class limits. Then the 9, the 19, and the 29, those are the upper class limits. And then the class width is if we look at our lower class limits, it's what we're going up by, essentially. So here we're doing 0 and we're adding 10 to get to 10. We add 10 again. So that means 10 is the class width. So it's not within a class. It's not 9 because each interval has 9. It's what you increase by from interval to interval. So 0 to 10, 10 to 20, we're going up by 10. 10 is the class width. Okay, so then once we have our intervals, our data is then sorted into these classes or intervals. Okay, so in a minute we're going to do a frequency and relative frequency table for our data that we collected on Friday with the texting. But first we got to talk about some good practices for constructing these tables or distributions. Remember, whenever you're asked to do a distribution, that's the same as me asking you to do a table for quantitative variables. So first, the classes should not overlap. Okay, so like going from 0 to 9 and then 10 to 19, right? We went from 9 to 10. We didn't say 0 to 10 and then 10 to 19. You can't have the same number in two different intervals because then if you have that data value, you won't know where to put it. Classes should not have any gaps. So you can't go from 0 to 9 and then skip down to like 12 to 19. You can't just skip numbers. Everything has to have a place. Classes should have the same width. So that just means each one is the same size. So like going up by 10 each time or going up by 5 each time, whatever you're doing, it has to stay consistent throughout your table. The class boundaries should be reasonable numbers. This is really just based on your minimum and maximum data values. So like if your minimum data value is 52, you don't have to start your table at 0 because that'll have a lot of emptiness before you get to any of your data values. Okay, so your class width, what you go up by, should be a reasonable number. If there's a logical class width, go with that. Or if you're not sure, just aim to have somewhere from 5 to 8 different intervals that you're sorting. It wouldn't make sense to just have like one interval with all your data in it because that won't tell you anything. Okay, so on the next page we have all our data that we got from both of my data analysis classes of our texting. So Tiffany was the fastest. I did put it in order for you, so it goes from 13.1 is the smallest value, and then as we go down to the bottom of our second column, 42 is the longest, so it goes in order. It won't always be in order, so make sure you always double check that the data you're looking at is actually in order. So if we start with 13.1 is our minimum, and 42 is our max. We could just start our intervals. We could do starting at 10, and we could go up by, let's see, because we got to go all the way to 42. So we could go up by 10s, to go from 10 to 50. But again, there's no really right or wrong way to do these classes as long as you have at least 5-ish. So we start with 10. Then that means if we're going up by 10, my next class, or my next interval would have to start at 20 if we add 10, 30, 40, 50. And so to figure out where these intervals go to or what that upper class limit is, again, it has to be right before the next lower class limit, and we can't overlap. So if we notice that we do have some decimal points in some of our answers, so we have to make sure that our upper class limits deal with those decimal points. The most we go to, though, is just to 1/10 to 1 decimal point, so we can go to 19.9. So really it's all going to be 0.9s. If we had 2 decimal places, you'd go to 19.99. If we had 3 decimal places, 19.999. But you have to have that decimal point. If you just said 10 to 19, then if we had like the data value of 19.7, we wouldn't know where to put it because it wouldn't be, that would be kind of in between 19 and 20, and we wouldn't have included that in our table. So then our next one, we can go to 20.9, to 30.9, to 40.9, oops, and then to 50.9. Oh, sorry, yep. Thank you, Joseph. Yep, 29, 39, 49, 59. My bad. 29.9, 39.9, 49.9, and 59.9. Thank you. Okay, so now for the frequency, now all we have to do is just count how many data values are in that interval. So from 10 to 19.9. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25. So lots of people in that range. So frequency would be 25. Okay, then from 20 to 29.9. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. Then 30 to 39.9. We have 1, 2, 3, 4, 5, 6, 7, 8. 40 to 49.9 just has that 1. And then we don't have anything from 50 to 59.9. Okay, so frequency is still just the number of data values that fall in our intervals. And we can find the relative frequency the same way that we did our relative frequency with our qualitative data. So we figure out how many total data values we have. So we just add up our frequencies here. We have 55. 55 total. So to do our relative frequency, you just take each frequency divided by the total. So 25 divided by 55. And then 21 divided by 55. 8 divided by 55. And 1 divided by 55. And 0 divided by 55. And again, you can write the relative frequencies as a decimal or a percent. Okay, so that's all the same as what we did last week with our qualitative data. You still just take the frequency for each of your intervals divided by the total. Okay, so this frequency and relative frequency distribution, pretty similar to last week. Do you guys have any questions? The main thing is just making sure with your upper class limits here that you just keep the same number of decimal places to make sure that none of your data values are excluded. Okay, so if we go on to the next page now, we're going to talk about histograms. So a histogram can be created from the frequency or relative frequency table, similar to how we created the bar graphs with our qualitative data. However, instead of our descriptive or qualitative categories, our categories are the classes that we used, or the intervals of data. Okay, so we're going to consider the data that we collected with our activity on Friday. We're going to construct a frequency histogram to represent our collected data. So here it says we're going to label our lower class limits of each class on our horizontal axis. So that's how we get our labels. So here we started with, we did 10, 20, 30, 40, and 50. So since 10 isn't 0, I can't put 10 right there on the origin. So I'm just going to scooch it over a little bit. So 10, 20, 30, 40, 50. And we do need to label our x-axis. So this is the texting speeds. And then our y-axis, similar to the bar graph, is going to be the frequency. Since we want a frequency histogram, if you were doing a relative frequency histogram, your y-axis would be the relative frequency. So in this case, our highest frequency that we have to deal with is 25. So we want to make sure that we go up that high. So again, this is our frequency. Want to make sure that we go up to 25, so we can maybe count by 5s. And then for the bars, we'll draw a rectangle whose width is the class width, so it'll go from 10 to 20. And then the height will be the frequency, again, or relative frequency if we were doing that. And then the difference, the main difference between a histogram and a bar graph is that with bar graphs, you had space in between each bar. For a histogram, the bars touch. So our first bar, 10 to 20, went up to 25, I think, right? Yep. So draw our bar, go up to 25, over to 20, come back down. Then our next class width from the 20 to 29.9 went up to 21. Bars touch. Then our next one was 8. And then our last one was 1. Now in this case, our very last interval, the 50 to 59.9, it's 0, so we don't have to draw a bar anyway. But if we did have some value there, like if the frequency was 2, you would still have to draw the bar and go over. You got to make sure you have a bar for everything you have. But again, in this case, it was 0, so we don't have that bar there. Okay, so again, main thing is bars touch for histograms. The height is how many data values were in that width. So our labels down here, again, you only use the lower class limits to label. So the label goes with the bar that's to the right. So this is the 10 to 10 point, or to 19.9, and then 20 to 29.9, 30 to 39.9. Okay. So again, the height tells you, so like here, when this one goes to 25, this is telling you that 25 people texted from 10 to 19.9 seconds. Okay, so the only issue with histograms is that you're not able to see the exact data values. You're just given a range. Same thing with the distribution. Like we know there were 25 people from 10 to 19.9, but we don't know the exact distribution in between there. We don't know how many people had 10, how many people had 15. We just know the range. So there are some ways that we can represent our data so that we can know the exact values. So if we move on here, on the next page, doing a stem and leaf plot. Sometimes they're also just called stem plots. The idea here is to split each data value into 2 parts, a stem and a leaf, hence the name, stem and leaf plot. The stem, so we have the data value of like 363. The stem is all of the digits in the value except the last one, so in this case 36 would be the stem. Then whatever the last digit is, or the rightmost digit, that would be the leaf. So we have our stem and leaf plot, we just have a vertical line. Our stems go on one side, on the left-hand side, and the leaves go on the right-hand side. And so the stems, just like with our classes and our histograms, you can't skip any, you just got to write them all down. And then the leaves are listed next to their stems in increasing order. So let's say we have the data values of like 36, 47, 45, and 52. If those are our data values, we wanted to write them as a stem and leaf plot. These, everything but the last digit, so the 3, 4, and 5, those would be our stems. And then for the leaves, we would take our last digit. So for 36, we have our 3 as our stem, the leaf would be 6. With the 40s, we have 2 numbers in the 40s, 47 and 45. They have to go in increasing order. So we'd put the 5 first and then the 7. And then we have our 52, so 2. Okay, you can also do stem and leaf plots with decimals. If we had like the data values 3.6 and 4.7, 4.5, 5.2. Where it could be helpful if you just put a decimal point kind of at the top. But you would still do it the same, where you'd have your stems, the first digit, 3, 4, 5, and your leaves would still be the last digit, which in this case is the number after the decimal point. If we do the decimal one, you're going to end up with a lot more stems, so it's not always the best way to represent data with whole numbers. It's less stems, so it's a little easier to organize. Okay. Back-to-back StemLeaf plots are also an option when comparing two different data sets, similar to like the side-by-side bar graphs that we did with qualitative data. This would just be like if we had some data for males of like 50, 52, and 64. And we have some female data, 48, 51, and 59. So if you wanted a way to compare these two different sets of data, you would have a stem in the middle, and then you'd have leaves on both sides, one for each of your groups here. So in this case, you can put males on the left, females on the right. So our stems now, we have to look at all of our data. So we have 5s and 6s for the males, 4, 5, and 5 for the females. So our lowest stem is 4. So we need to go up to 6. So 4, 5, and 6. These are stems. And then the leaves. So for the males, they're going to look backwards when you're doing the stems because it's going to be on the left side instead of the right side, but it still means the same thing. So for 48, 4 is our stem, 8 would be the leaf that would go to the left there. And then for the, oh wait, that's female, sorry. Males would be 50. 50 and then 52, again still in increasing order as you go away from the stem, and then 64. And then the females would be 48 and 51 and 59. Okay, so just a way to compare two different sets of data similar to like the side-by-side bar graph. Go ahead and go to lunch. So to do the stem and leaf plot here, I'm not going to ask you to do it for all 50 whatever pieces of data. Joseph, find your seat, please. Nope, now. Now. So you don't have to do all of the data values. Let's just do, we'll do the first row. So we'll just do the first half here when we do our stem and leaf. Well, that's a highlighter. Okay. We'll do just our first half of the data when we do our stem and leaf plot. So if we look our minimum value, and I say on the packet, we're going to round to the nearest second, just so we don't have to worry about the decimal points. So we go from 13 to 22 if we do our rounding. So when we have our stem and leaf plot. So since our lowest one is 13, our highest one is 22, our stems are just going to be 1 and 2. So fun. Since we're only doing half of our data, the bottom half of our data. And so I put them in order already for you, so I'll just leave this up here so you guys can do the stem and leaf plot. So like our first stem was 1, so we have to do all of the data points that start with a 1 there. So from the 13 all the way down to the 19. So we would have your first leaf would be 3 for 13. And then next to it there's two 14.1s, so rounded, those would both be 14, so you have 4, 4 right next to it. And then we have 1 15 point. We're rounding to the nearest second. Yeah.
Is there a reason you only did half of it?
Just because there's 50 some data points, so we don't have to use the time right now to do that. Then you'd have your 6s. So there's 3 16s, so 6, 6, 6. The 16.5 would be rounded up to 17. So you'd have 7, 7, 7, 7, 7. For all those 17s and the 17.1. Then the 17.5, the 0.7, and the 0.8, those would all get rounded up to 18, so you'd have 18, 18, 8, or 8, 8, 8, 8, 8, 8, 8.
Round up.
Yeah, we're just rounding to the nearest second for here, so we don't have too many decimals. And then our last couple here. So then the 18.6s will get rounded up to 19, so I have 9, 9, 9, 9. Our 19.9s will get rounded up to 20, so you'll have a 0 for the 20. And then the 20.3s will be rounded to 20 as well, so zeros. And then the 21.6 will get rounded up to 22. Okay, so yes, it's a nice long list. But basically, again, stem and leaf plots, the stem is everything but the last digit. Leaf is the last digit. Okay. Questions on stem and leaf plots? I know I didn't write it down, but I wanted you guys to not have to flip back and forth for the data. So our last one here we're going to talk about is a dot plot. Again, this is another way where you can see the exact values, unlike with the histogram or the distribution. So for dot plots, you create a number line labeled as you would an x-axis, or the y. No, it should be x-axis. This should be x-axis, not a y-axis. That's my bad. The x-axis of a histogram to fit the range of your data value. So again, just make sure that whatever your min and max data value are, they would fit on that number line. And you label with even increments. You can't skip any values. Then on that number line, you just place a dot for every data value that you have. So for our example, we have our number line. This is just a rough, general example for a dot plot. You would go from, if we had the data values of like 6, 7, 7, 9, you could label from 5 to 10. And then you would just put a dot, or some people do X's, it's the same thing, above wherever the data value is. So for 6, put a dot above 6. For 7, we have 2 of them, so you put 2 dots above 7. And we have 1 9, so 9 gets 1 dot. Bless you. Okay, so for our data, we have to go from, what's our maximum again? From like 13 to 43. So we do our number line here. You can start with 13. And we could go up by 5s. Okay, and then you can do like the little tick marks in between if you want to help you when you're doing your dot plot, but you don't have to, as long as there's space for all of them. And then again, you just put dots over wherever our data is. So we'll just do the first couple just to get an idea. Dot plots are pretty straightforward and we don't need to spend our time doing all 55 data values. So like 13.1, and then we have two 14.1s. So if we go down, we do lots of flipping here. So 13.1, right next to 13. Then we have two 14.1s. Then we have 15.1 and 3/16. So you kind of get the gist. It's just a dot for every single data value. Dot plots are a way where you can specifically see each exact data point or data value, whereas with the histogram, it was just, here's a range, there's this many in this range. So histograms are nice for a summary. They give you a general idea of where your data is, but if you need you need to know the exact values, then dot plots or StemLeaf plots are your best bet. Okay. Do you guys have any questions on histograms, StemLeaf plots, or dot plots? Okay. Then